The dream of mining asteroids for precious metals is a strategic miscalculation of their true value. Humanity's future in space won't be built on gold or platinum brought back to Earth. It will be built from the most common, overlooked materials in the solar system: rock, dust, and ice. The simulation ran for 3 days, a silent, accelerated lifetime of engineering trade-offs and logistical impossibilities. On the main screen in the darkened lab at the Colorado School of Mines, the Martian outpost was a ghost of its former self. Dr. Kenji Tanaka watched as the final components vanished, stripped away by an optimization algorithm that had turned cannibalistic. What began as a blueprint for a self-sustaining habitat for 12 had been whittled down to a single lander, its payload capacity reduced to 0. It was a mathematically sound model that demonstrated the mission's inherent unviability. A line of red text blinked at the bottom of the display. Mass budget exceeded. The launch unviable. Kenji leaned back, the faint whir of the server racks the only sound in the room. He traced a finger over a cascading dependency chart on a secondary monitor. It was a spiderweb of interconnected calculations, and at its center was the launch vehicle. The initial sin was a solar panel array. The mission planners had requested a 10% power redundancy, a seemingly minor adjustment. The extra panels added 80 kilograms. To lift those kilograms out of Earth's gravity well, the second stage of the launch vehicle required more propellant. That propellant had mass of its own, which in turn demanded stronger, heavier tanks to contain it. The mass penalties compounded. The heavier tanks required reinforced structural supports for the launch vehicle. More mass. The reinforced structure needed a more powerful first-stage engine burn. More propellant. Each solution compounded the problem in an exponential, unforgiving climb. He watched the algorithm's logic play out in reverse. To make the launch viable, it first sacrificed the redundant power system, then the primary science lab, then the living quarters, the water reclaimers, and the radiation shielding. Every kilogram shaved off the top required tons to be removed from the bottom. This was the brute force reality that lurked beneath every ambitious blueprint for space exploration. It wasn't about the vast, empty distances between worlds. It was about the first 100 kilometers straight up. The climb out of the gravity well was a toll. The price: mass. The rocket equation was not a formula. It was a tyrant, and it governed every decision with absolute authority. For decades, the only response had been to build bigger rockets, to brute force a solution by pouring more energy and resources into fighting gravity. Kenji closed the failed simulation, the screen returning to a neutral black. The pristine vision of a Martian settlement was gone, erased by the physics of its own creation. His team wasn't trying to build a better engine or discover a lighter alloy. They were chasing incremental gains in a game that was fundamentally rigged against them. The entire paradigm was wrong. They were trying to ship a mountain across an ocean, one spoonful at a time, when the real solution was to learn how to build with the materials already on the other side. He minimized the launch vehicle schematics and opened a different file, a simple, unadorned orbital plot of near-Earth objects. A swarm of tiny points drifting in the void. The problem. It wasn't the rocket. The problem was that they were still trying to bring everything with them from Earth. The Mars simulation remained a scar on the lab's central server, a digital monument to a dead-end approach. Kenji Tanaka had his team redirect every available processing cycle to a new target. Instead of modeling descent vectors and habitat assembly, they were now processing raw light, sifting through terabytes of spectral data from ground-based telescopes aimed at 1,000 different points of light. Each one was a near-Earth asteroid, a silent remnant from the solar system's formation. Michael Torres, a doctoral candidate whose focus was on resource extraction modeling, stood beside Kenji's desk, pointing to a highlighted anomaly on his tablet. "This is the 5th C-type we've analyzed with this exact signature," Michael said, his voice low and focused. "The absorption band at 3 micrometers is deeper than the models predicted. It's screaming hydration." On the larger screen, Kenji pulled up a comparative analysis. On one side was the spectral profile of 16 Psyche, an M-type asteroid whose data showed an overwhelming signature of iron and nickel. It was the media darling, the trillion-dollar space rock that promised a new gold rush. On the other side was the data from the carbonaceous asteroids Michael had flagged, dark, primitive, and seemingly unremarkable. They were little more than cosmic rubble. The money is in 16 Psyche, Kenji mused, more to himself than to Michael. That's what everyone is chasing, a mountain of metal. It's a mountain we can't move or refine with any current technology, Michael countered, swiping on his tablet to display a new dataset. It's a destination. These C-types, they're a supply chain. He brought up the final public reports from the osiris-rex and Hayabusa 2 missions. The Japanese probe had brought back a few grams of dust that were darker than charcoal, rich in organic molecules, and most importantly, water, locked away inside clay minerals. The American mission had found the same thing. The samples were archives, holding the pristine building blocks of planets. Kenji stared at the chemical breakdowns. Carbon, nitrogen, phosphorus, and water, up to 20% by mass in some of the hydrated minerals. It wasn't liquid, not a convenient ice field, but it was there, infused into the very rock and dust. He cross-referenced the sample data with the spectral signatures Michael had found. They matched. The unassuming dark asteroids were soaked with the most valuable substance in space. The pieces clicked into place, rearranging the entire problem. The failed Mars simulation had collapsed because of the mass of its fuel, its water, and its structural components. Every kilogram was a crushing weight on the launch manifest. But here, drifting in easily accessible orbits, were repositories of everything they needed. The water wasn't just for life support. It could be split through electrolysis into hydrogen and oxygen, the most powerful chemical rocket propellant known. The loose regolith, a mix of silicates and carbon compounds, was littered with grains of nickel iron, raw feedstock for 3D printing and construction. They had been trying to haul a hardware store to a construction site, when the site itself was sitting on a quarry. The race for 16 Psyche was a hunt for treasure to bring home to Earth. This was different. This was about finding the raw materials to never have to go home again. The theoretical work was done. The spectral data had pointed the way, and the sample return missions had confirmed the ground truth. Now, the quiet hum of the lab at the Colorado School of Mines was the sound of engineering. Dr. Kenji Tanaka's team had traded celestial mechanics for industrial process modeling. Their new simulation was not a grand architecture of interplanetary settlement, but a microscopic focus on a single robotic pioneer touching down on a simulated C-type asteroid. On the main display, a virtual lander, all spindly legs and functional boxes, settled onto a landscape of charcoal grey regolith. Michael Torres sat at the console, his fingers moving across the keyboard, initiating the first sequence. "Deploying concentrators," he announced, though only Kenji was in the room with him. From the lander's main body, a set of highly polished parabolic mirrors unfolded like the petals of a metallic flower. They tilted, catching the harsh, unfiltered sunlight of the simulation and focusing it into a single, needle-thin point of intense energy on the ground below. The regolith at the focal point began to glow, its temperature climbing rapidly past the boiling point of water. There was no atmospheric haze, no diffusion, just pure, concentrated thermal power. A faint cloud of vapor erupted from the heated patch of dust. "Capture efficiency is nominal," Michael reported, nodding at a graph plotting molecular density against time. A domed collector hood had descended over the area, trapping the outgassed water vapor. Inside the collector, a cryocooler instantly froze the vapor onto collecting plates, turning it into a fine frost. "We're sublimating the water directly from the hydrated clays. It's slow, but it's steady." Kenji watched the telemetry. The process was not elegant, but it was relentless. Gram by gram, the lander was harvesting water, the most critical resource for both life and propulsion from otherwise inert rock. The simulation calculated the energy budget. Solar power was effectively infinite, and the only consumable was time. After an accelerated hour, Michael initiated the second phase. A small, wheeled rover detached from the lander's side and trundled away across the dusty surface. It was a simple machine, little more than a rolling magnetic drum. As it moved, it kicked up the fine regolith. Most of the dark dust simply fell away, but tiny, slightly more lustrous flecks clung to the drum, separated from the silicates by a fundamental force of nature. Magnetic separation is yielding about 4% nickel-iron content from the fines, Michael said, zooming in on the rover's collection bin. It's not high-grade ore, but it's pre-processed and requires almost no energy. The rover returned to the lander and deposited its payload of metallic grains into a hopper. The final sequence began. Inside a small insulated chamber, an electron beam generator powered on. It aimed a focused stream of electrons at a thin layer of the collected powder, melting it instantly. The beam moved, tracing a cross-section, and another layer of powder was added. Layer by agonizingly slow layer, a solid object was being built from the refined dust of the asteroid itself. They let the simulation run for a full day cycle. When it concluded, the final rendered image appeared on the screen. The lander stood silently on the gray plain. Its propellant tanks were 12% fuller than when it had landed. The little rover was docked in its bay, and floating just above the surface, held by a simple tether, was a single 1-meter I-beam. It was unrefined, its surface rough, but its geometry was perfect. It was a piece of industrial hardware, forged in vacuum from the raw materials of space. They hadn't brought anything back to Earth. They had turned a dead rock into a factory. The final slide of the presentation was not a chart or a block of text. It was the image from the simulation. The lonely robotic lander on its gray patch of asteroid, and the single, crudely forged I-beam tethered beside it. In the sterile quiet of the conference room at the Colorado School of Mines, Dr. Kenji Tanaka let the image hang in the air for a long moment. His audience, a curated mix of aerospace executives, venture capitalists, and agency program directors, watched the screen with an unnerving stillness. For 60 years, every calculation in human spaceflight has been anchored to a single, brutal number, Kenji began, his voice even and measured. The cost to lift 1 kilogram of mass from the surface of Earth into orbit. This number has dictated the size of our ships, the scope of our missions, and the limits of our ambitions. We have treated space as a destination to which we must carry everything we need. He gestured to the screen, to the solitary beam. This changes the equation. The value of this beam is not what it would be worth if we brought it back here. Its value is fundamentally transformative because it is already there. It is the first brick. Michael Torres stepped forward to a secondary podium, bringing up a simple table of figures. Our models, based on the confirmed regolith composition from missions like osiris-rex and Hayabusa 2, show that a C-type asteroid in an accessible orbit contains more water than has ever been launched into space in the entire history of the space program. That water, when separated into hydrogen and oxygen, represents a fully stocked orbital propellant depot. A hand went up in the front row. It was a senior engineer from a legacy aerospace firm. Dr. Tanaka, the energy costs for that level of processing, the logistics of setting up a refinery on a zero-G body, the challenges are monumental. They are, Kenji agreed without hesitation, but they are engineering challenges, not fundamental physical barriers. We are no longer fighting the tyranny of the rocket equation. We are facing a logistics problem, and logistics problems can be solved. The alternative is to accept that a permanent, large-scale human presence beyond Earth is impossible. He switched the slide. A new simulation appeared, this one a rapid, time-lapsed animation. An asteroid was gradually disassembled by a swarm of autonomous robots. The harvested water was stored in orbital tanks. The refined metals were fed into larger 3D printers, which extruded the trusses and panels for a massive solar power array. Its surface area measured in square kilometers. Another animation showed thick walls being printed from unrefined regolith, forming a habitat module whose sheer mass provided radiation shielding that no ship launched from Earth could ever carry. The conversation is no longer about the market for platinum on Earth, Kenji continued, his voice rising with controlled intensity. It's about the strategic value of an orbital refueling station that can send a mission to Jupiter without a multi-billion-dollar launch. It's about building telescopes with apertures 10 times the size of Webb because we don't have to fold them into a fairing. It's about building our infrastructure in space, for space. A silence descended on the room, thicker than before. It was the sound of decades of assumptions being re-evaluated. The dream of mining 16 Psyche for its precious metals was a child's fantasy of treasure chests. This was a plan for building a new continent, a new industrial revolution floating in the void. It was high risk, high capital, and decades away from fruition. But for the first time, it was not impossible. It was an engineering pathway. As the presentation concluded, there was a perfunctory round of applause, but Kenji watched as the real reactions unfolded. No one rushed the stage with questions. Instead, they turned to each other in quiet murmurs. Phones emerged from pockets. A venture capitalist gave a sharp, almost imperceptible nod to his associate. The race wouldn't be announced on television or marked by rocket launches. It would begin in rooms like this, with quiet calculations and the silent wiring of funds. The frontier had not just been opened, its very nature had been redefined. The challenge was no longer how to escape Earth's gravity, but what to build once you had. The most profound revolutions often begin not with a bang, but with a quiet shift in perspective. The journey from a failed Martian simulation to a single space-forged beam redefines our entire future beyond this world. We learned that humanity's next chapter won't be financed by gold or platinum, but built from the humble rock, dust, and ice that have been waiting for us all along. If this story made you look at the night sky a little differently, make sure you're subscribed to Tech Dissect Official for more explorations of our technological future. As this new race begins, driven by private ventures and national interests, it raises a critical question. Who do you believe should own and control the resources found on an asteroid? The company that gets there first, or an international body representing all of humanity? Thanks for joining us for this dissection, and we'll see you on the next one. As this race for the solar system's resources heats up, the greatest challenge might not be the engineering, but the treaties we fail to write before the first drill touches down.